All right, good morning. What I'll do today is LHospitals Rule. There's 7 different kinds of indeterminate forms. We'll do most of them today. If not, we'll spill over a little bit to next Tuesday, but I should get most of them today. So the first 2 major kinds are 0 over 0 type and infinity over infinity type. What this is doing is we have struggle between functions. So even just as I look at this, well, one of the good things to notice is if you have a function which goes to 0 as you approach a, then 1 over the function goes to infinity and vice versa. So note, I guess, before we start, if we have a function f of x such that the limit as x approaches a of f of x is 0, then the limit as x approaches a of 1 over f of x is plus or minus infinity. Doesn't matter which one it blows up. We'd have to check specifically whether it blows up positive or blows up positive, and vice versa. I.e., if we have the limit as x approaches a of f of x is plus or minus infinity, then the limit as x approaches a of 1 over f of x is equal to 0. You don't have to go very far. Why I'm going to notice this is because 0 times infinity type is infinity over infinity or 0 over 0. You can create both in a second when we get there. So for an example, if f of x is x squared, then 1 over f of x is 1 over x squared. So 1, if I have that the limit as x approaches 0 of x squared is 0 squared, which is 0, implies that the limit as x approaches 0 of 1 over x squared is positive infinity from the left and the right. I'm not checking the limits, but this is what it is. The left-hand limit equals the right-hand limit. So as I approach there, my limit is 0. And 1 over x squared as I approach 0 is going to blow up. And 2, as I approach, if I look at now, if f of x is 1 over x, or actually it doesn't matter, I can keep the same one. The limit as x approaches infinity now of x squared is positive infinity, and therefore it follows that the limit as x approaches infinity of 1 over x squared is equal to 0. This is happening for the green ones. What we're talking about is near 0. That's what's happening. That's these 2 limits. And for the pink ones, these 2 limits are describing this scenario. So this is useful to know. 1 over f goes to 0 if f goes to infinity, and if f goes to 0, 1 over f is going to go to infinity. Theorem. L'Hopital. It's not really L'Hopital, it was Bernoulli. L'Hopital was a French aristocrat. Bernoulli was the smart guy, Johann and Jacob. I think it was Jacob that did this. But so the story goes is L'Hopital wants his name in history and the math, and Bernoulli is the one that actually proves everything, but L'Hopital gives him a bunch of money so that he can live the end of his life in luxury. And in exchange, Bernoulli gives him his next mathematical result. His next mathematical result is this statement called, now in 2022, L'Hospital's rule, but it's Bernoulli's rule for limits in indeterminate forms. So let f and g be differentiable functions. On open interval with a inside there be such that f of a equals 0 and g of a equals 0 and g prime of x is not 0 or x not equal a. Then what this says is, if we have 0 over 0 type, a limit as x approaches a of f of x over g of x, that ratio in limit is exactly the same as the ratio of their derivatives. So the limit as x approaches a of the ratio of the functions, if you have 0 over 0 type, is what we're going to call it by L'Hopital's rule, this will be equal to the limit as x approaches a of f prime of x over g prime of x. This is not the quotient rule. We're not taking bottom d top minus top d bottom over bottom squared. I'm taking the derivative of the top and the derivative of the bottom separately. That ratio is the same. This is L'Hopital's rule. You can only take the derivative in two forms, in this form or in the next form. When we do this, will be infinity over infinity. But let's do some examples first of this first kind. So this is the first kind, type 1. Infinity over infinity type. So example. The first one, the easiest one is, recall the limit as x approaches 0 of sine x over x equals 1 by the squeeze theorem, etc. in math 114. But now all I have to do, now we have sine of 0 equals 0 and x equals 0. So does that tell us we have 0 over 0 type? So we have the limit as x approaches 0 of sine x over x is 0 over 0 type. So this is equal to, by L'Hopital's rule, the limit as x approaches 0 of cos x over 1, which is cos of 0, which is 1. So I'm allowed to take the derivative of the top and the bottom, and it will simplify the expression usually. Sometimes you have to apply the rule more than once, but otherwise we just get a much simpler answer. Example 2. Is there one that I have to give it more than once? Yeah. Okay. So what if I have the limit as x approaches 0 of the square root of 1 plus x minus 1 over x first of all, again, I'm putting this in. These are all going to be 0 over 0 type because I just talked about doing this section 0 over 0 type. But this is 0 over 0 type. I check the two functions, which equals, therefore, by LHospitals rule, because I've checked that you have 0 over 0 type, this will be equal to what? I have to take the derivative of the top and the derivative of the bottom. The derivative of the top is going to be 1 over 2 root 1 plus x over 1 is essentially what we've done. This equals, just by cleaning it up, the limit as x approaches 0 of 1 over 2 root 1 plus x. There's no problem anymore, so this turns into 1 over 2 root 1 plus 0, which is 1/2. So there's an infinite struggle here, or a tug of war is what's happening. We want to know, and that ratio, 1 is trying to blow up to infinity because we get 0 over 0 type. And so we need to know whether we're going to infinity or whether we're going to 0. In this case, they balanced off to give us 1/2. Example 3, we may have to do this more than once. So if I have the limit as x approaches 0 of x minus sine x over x cubed, I check this is 0 over 0 type. And so I can use LHospitals rule. LHospitals rule therefore tells me that this is the limit as x approaches 0 of 1 minus cos x over 3x squared. This is still 0 over 0 type. Cos of 0 is 1, 1 minus 1 is 0, so I'm still going to get 0 over 0 type. So I can use LHospitals rule again. Is the limit as x approaches 0 of, now I'm going to get sine x over 6x. This is sine x over x, or I can write this as 1 over 6, the limit as x approaches 0 of sine x over x. This is, once again, like we did the first time, 0 over 0 type. So I don't even want to be fancy. This just says that this will be 1 over 6, the limit as x approaches 0 of cos x over 1, which is, of course, 1 over 6. Hey, we the kitty. We the kitty. So this is LHospitals rule, infinity over infinity, or 0 over 0 type. The next kind that we're going to have is, I'll keep the examples fairly easy. Some of these functions can get nasty depending on, so they'll be like, oh, this is easy now. Well, it's like, yeah, but what we're doing is we're giving you new machinery to compute these newer transcendental functions, and so that we can compute the limits. This is an extremely useful tool. It will be extremely easy when we use this tool on simple functions. I may or may not be allergic to all the cats that come up here. As soon as she's up here now, she makes me sneeze. Kitty. Hey. She's messing with all the cords in the back of the computer right now. But once we start using larger functions and more horrible functions, these derivatives can still be lame. I won't do one right now. We'll do one near the end. Okay, I won't do any scary ones yet. So, theorem. This will be infinity over infinity type. These two theorems are the only way, again, that you're actually allowed to take the derivative of the top and the bottom if you have 0 over 0 or infinity over infinity. So what's it going to say? Let f and g be differentiable in an open interval with a inside there, be such that f of x goes towards plus or minus infinity and g of x tends towards plus or minus infinity as x approaches a, and that g prime of x is not 0 for x not equal a, near a in this interval, then we have the same thing. The limit of the functions ratio is equal to the limit of the derivatives ratio. The limit as x approaches a of f of x over g of x is equal to, by LHospitals rule, if this is infinity over infinity type, we can write this as the limit as x approaches a of f prime of x over g prime of x. This also works when we have infinity over infinity type. These are the two cases that we're allowed to actually take the derivative. There's 5 other indeterminate forms: 0 times infinity, which is either you can turn it into both infinity over infinity type or 0 over 0 type. Then there's infinity minus infinity. Then there's 3 exponential types, which we're going to use a trick similar to logarithmic differentiation. Example 4. Let's do the limit as x approaches pi over 2 minus of secant x over 1 plus tan x. So if we look at secant, remember this one's a little bit harder because you have to picture the functions, but if you look at pi over 2, what I'm doing in my head is picturing these functions. So tan looks like this. 1 plus tan is just going to be shifted up 1, which is still going to go to infinity at pi over 2. And then secant is going to be this guy. So we're describing this pi over 2 from below, pi over 2 from below. This gives me positive infinity is what I'm saying. So this is infinity over infinity type. So the limit as x approaches pi over 2 from below of secant x over 1 plus tan x is equal to, by LHospitals rule, because I have infinity over infinity type this time, this is equal to the derivatives, which is going to be, you have to write out the limit every time. The limit as x approaches pi over 2 from below of secant x tan x over secant squared x. If you simplify this, this is just going to give me what? This is equal to the limit as x approaches pi over 2 minus of just sine x. Secant, one of the secants cancels outright, and then secant is 1 over cos. So 1 over is going to be cos, and then tan is sine over cos. So all the coses cancel here. And I'm just left with sine, which equals sine of pi over 2, which is 1. Example 5. Let's do that one. Yeah, okay, I'll do that one next. The limit as x approaches 0 of the natural log of x over 2 root x. What is this? We know that log goes to infinity as x goes to, I should say infinity. Otherwise, I'd have to have 0 plus. But as x goes to infinity, log x goes to infinity, and root 2x or 2 root x goes to infinity as well. So this is infinity over infinity type. So this is equal to, by LHospitals rule, the limit as x approaches infinity. Now I can take the derivative of the top, which is just 1 over x, over the derivative of the bottom, which is going to be 2 over 2 root x. So these 2's cancel, which is equal to the limit as x approaches infinity of 1 over x times root x. I'm just simplifying now. This is equal to the limit as x approaches infinity of 1 over x to the 1/2, which is equal to 0. How do I know this? Because 1 over any of these guys should go to 0. They all do this. They're all reciprocal functions. Yeah, let's do one more. What we're also doing is we can show that e to the ax, where a is a positive real number, eventually grows faster than all other polynomials. Dominates, essentially, is what we call it. Grows faster than any polynomial. I.e., show that the limit as x approaches infinity of e to the, let's do it this way, of x to the n over e to the ax equals 0. Hence, if you look at this, x to the n is trying to go to infinity as x goes to positive infinity. E to the ax is also trying to go to infinity. So 1 over e to the ax, if you look at x to the n, at infinity, it's going to be with a number 1 in the front. It doesn't matter what whether n is odd or even, it's going to go to positive infinity. When I look at e to the ax, also positive infinity, we're going to go to. If I do 1 over this guy, one over e to the ax is e to the negative ax, which is this guy, which says it will go to 0. And so what I want is, I have a war between these two functions. We're comparing this one versus this one. Now I have a tug of war, and I have this ratio. 1 over e is trying to go to 0. X to the n is trying to go to positive infinity. And this is indeterminate. And I'm going to use LHospitals rule to show that this limit is 0, which means e to the ax, 1 over e to the ax wins this tug of war and goes to 0. It doesn't blow up to infinity, which says, long story short, that if e isn't growing faster than the polynomial would have won the tug of war and the limit would have gone to infinity. Instead, e is winning the tug of war and it's going to go to 0. And therefore, e eventually will grow faster than all polynomials. Polynomials are linear combinations of powers of x, but in limits at infinity, they're dominated by their leading term, x to the n. So this is what it's really saying mathematically, that e will grow faster eventually than any polynomial. So indeed. technically I have to show that use induction, but I'll get rid of it here. So we have the limit as n approaches, or sorry, as x approaches infinity of x to the n over e to the ax. This is infinity over infinity type. So by LHospitals rule, this is equal to the limit as x approaches infinity of n times x to the n minus 1 over a e to the ax. I just take the derivative of the top and the bottom. Well, this is still infinity over infinity type. And so I'll do it again. This is equal to LHospitals rule, the limit as x approaches infinity of n minus 1, x to the n minus 2 over a squared e to the ax. Those are just numbers. X to the n minus 2 still goes to infinity. E to the ax still goes to infinity, whether they're multiplied by numbers. So this is once again infinity over infinity type. I can take the derivative again. You'll see where I'm going with this in a second. Limit as x approaches infinity of n minus 1, n minus 2, x to the n minus 3 over a cubed e to the ax, which is still infinity over infinity type. So we're going to do this. We need induction. You don't know what mathematical induction is. We're not going to do it in this class. Shows this will imply that the derivative of x to the n, the nth derivative of x to the n is n factorial. And the nth derivative of e to the ax is a to the n e to the ax. But it is, so what do we get after we take the derivative n times by LHospitals rule? We're going to get the limit as n approaches infinity of n times n minus 1 times 3 times 2 times 1 over a to the n e to the ax. So when we take the derivative, we get all the exponents down, which is when we multiply those together, we call that n factorial. Every time I take the derivative of e, I get an a in there by the chain rule. And so this is equal to now n factorial over a to the n times the limit as x approaches infinity of e to the negative ax 1 over a to the x, which is n factorial over a to the n times 0, which is 0. So by n applications of LHospitals rule and using some induction clever tricks, I didn't actually prove them, but it's not that bad. We can show that e grows faster than all polynomials eventually. Eventually, e will dominate them all. All right. So the next two kinds are sort of just using algebra to clean everything up. So we have, let's do 0 times infinity type and infinity minus infinity type. These are the next two kinds. So what are these going to say? What we're going to have here is if we have the limit as x approaches a of f of x times g of x with f of a equals 0 and g of x tends towards infinity, then what we're going to do is we really have two cases. If or vice versa. Plus or minus infinity, doesn't matter which one. So one of them blows up and one of them goes to infinity. If without loss of generality, we just assume this case, then we have two cases. I can turn it into both infinity over infinity or 0 over 0 type. And notice that even if I have a number, 1 over 2 is equal to 2. And similarly, 1 over f of x is equal to f of x. This will be extremely useful. 1 over g of x is equal to g of x. So I'm just using the inverse of an inverse is the function again, or the inverse of the inverse, the reciprocal of the reciprocal is the function. 1 over half or 2 is just 2 again. Why is this useful? Then I can turn this limit into the limit as x approaches a of f of x over g of x. I can write as the limit as x approaches a of g of x over 1 over f of x. Why does that help me? Well, if this was 0 times infinity type, what that now gives me is if f was going to 0 at a, 1 over f goes to infinity. And this was the key right at the beginning. This is why I went over this up here. Where was it? Way at the beginning. If f is going to 0, 1 over f has to blow up to infinity. Why does that help us now? Well, now that says, what did that just turn this into? This just turned this into infinity over infinity type. And then I can use LHospitals rule. Or I can write it as equally true, limit as x approaches a of f of x over g of x. If this is 0 times infinity type, if g goes to infinity at a, 1 over g goes to 0. This equals the limit as x approaches a of now f of x over 1 over g of x. I've just done 1 over g or 1 over f. But now what does that give me? That gives me 0 over 0 type. And then I can use LHospitals rule. So that's exactly what's happening here. Why would I ever do this? Well, again, the idea is one is trying to go to 0 and one is trying to blow up to infinity. And we have this tug of war. But sometimes if I have a choice now, people will often ask, well, which one should I use, 1 over f or 1 over g? It doesn't really matter whether I create infinity over infinity or 0 over 0. Both LHospitals theorems say that we can take the derivative if you have either kind of those. What you want to do is make functions which are on the top and the bottom, which are nicer to take the derivatives of. Let's do an example and I'll show you. Example 7, I believe. So compute the limit as x approaches 0 plus of root x times log x. This is going to 0. This is going to negative infinity. So this is, it doesn't matter whether it's positive or negative infinity, just blowing up. So this is 0 times negative infinity type. I can write this as the limit as x approaches 0 plus of log x over 1 over root x to give me, what did I get? Infinity over infinity type. Or I could equally write this as the limit as x approaches 0 plus of root x times log x is equal to the limit as x approaches 0 plus of root x over 1 over ln x, which will be 0 over 0 type. Which one am I going to choose? Which one would you choose? Do you want to take the derivative of 1 over log? Because that's log to the minus 1. And then I'm going to, it seems like this second one is harder to take the derivatives. So I'm going to pick the first one. So the limit as x approaches 0 plus of root x log x is equal to the limit as x approaches 0 plus of log x over 1 over root x, which I can write as, this is now, I just did that so that I would have exactly infinity over infinity type. So then I can take the derivative. This equals now by LHospitals rule. I can take the derivative. This is the limit as x approaches 0 plus of the derivative of the top is 1 over x over the bottom, which is just going to be x to the negative 1/2, which will be negative 1/2 x to the negative 3/2. When I clean this up now, I'm just going to write this as -2, the limit as x approaches 0 plus of, we're going to get x to the 3 over 2 over x. I'm just 1 over x goes to the bottom, the negative I bring to the top of the exponent. This is equal to -2, the limit as x approaches 0 plus of root x, which is -2 times root 0, which is 0. TD Bank's harassing me. So this is how we compute 0 times infinity. I pick, the moral of the story is whichever one is easier, I can turn it into infinity over infinity or 0 over 0 type by using this clever 1 over 1 over trick. But once I do that, I'm usually just picking the one which gives me the nicer derivatives to compute. Yeah, I only have 10 minutes left, so let's do infinity over infinity type. So if we have infinity minus infinity, we use algebra to turn it into 0 over 0, infinity over infinity, or 0 times infinity type, because then we know how to deal with this. If we get 0 times infinity, we can do this the same trick as we just used. If we get 0 over 0 or infinity, we're already ready to take the derivative. So what does this look like? These ones are best done with just using an example. Is this one? Yeah, let's do the limit as x approaches 0 plus of cosecant x minus 1 over x. Now, you have to view this. Sometimes the functions we give you, again, aren't going to be the easiest ones to picture, but cosecant as I approach 0 blows up to infinity, and 1 over x as I try to approach 0 from above is infinity. So this is definitely infinity minus infinity type. What I want to do is turn everything into sine and cos. This is equal to limit as x approaches 0 plus. How do I use algebra? Well, I have a fraction here. The other one's also a fraction. It turns out this is 1 over sine x minus 1 over x. I want to get a common denominator. This is going to equal, here I'm missing x. And here I'm missing sine. So I'll multiply by what I'm missing to get a common denominator. Once I get the common denominator, this equals now the limit as x approaches 0 plus of x minus sine x over x times sine x. This is now, as you'll see, x is 0 when x is 0. Sine of x 0 is 0. So this is 0 on the top over 0 times 0, which is 0. So this is 0 over 0 type. So this says now, after I've used algebra, it turned it into a 0 over 0 type. Therefore, I can use LHospitals rule to take the derivative. This gives me on the top limit as x approaches 0 plus of 1 minus cos x over, now we're going to use the product rule, sine x plus x cos x. If I look at this again, where am I going? I'm going to 0. This is still going to be 0 over 0 type. Anytime I reassess and simplify and I get 0 over 0, infinity over infinity, I can take the derivative again. So I will take the derivative again. So this equals, by LHospitals rule again, the limit as x approaches 0 plus of, what do I get? Negative sine x on the top, or sorry, just sine x on the top. And then I'm going to get cos x plus x sine, sorry, plus, let's leave, so we'll get cos x minus x sine x, which is just simplifying the limit as x approaches 0 plus sine x over 2 cos x minus x sine x. The idea is now I don't have in 0 over 0 type, I have zero over 2 type, which is not LHospitals. You can just compute at this stage, 0. Let me try to squish in the idea. I have 5 minutes. Let me try to squish in the last 3 times the one to infinity, 0 to the 0, 0 to, or infinity to the 0 type. These are the last 3, so that's all 7. So we have 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity. Those are the first 4. Basically, if you have 0 times infinity or infinity minus infinity, I use algebra to clean it up and give myself 0 over 0 or infinity over infinity. Once I have that, I can take LHospitals rule and take the derivatives and get the limit usually, even if I have to do it more than once. These ones are explicitly saying that we have y equals f of x to the g of x is what we're explicitly saying here. And so we have the limit as x approaches a of y is equal to the limit as x approaches a of f of x to the power g of x. And say, for example, we get 1 to the infinity type. Then this says f of x is tending towards 1 and g of x is tending towards infinity plus or minus as x approaches a. We want to know how to rectify this. What we're going to cleverly do is call it y and use exponent laws or logarithm laws. Then y equals f of x to the g of x implies that log of y is equal to log of f of x power g of x. Exponent on the inside becomes number on the outside. This should be g of x times f. This is extremely useful for us, except you have to be careful. We have to take the exponential at the end. This says that the limit as x approaches a of log y, not y anymore. We want the limit of y. But we're now computing the limit of log y, but this gives us a way of computing. This will be the limit as x approaches a of g of x times log of f of x, but where was f of x going? F of x was going to 1. So this will be going to 0. And where was g going to? Infinity. This is 0 times infinity type. So the idea is once I do that, then I compute the limit. If this equals L eventually, then we get the limit as x approaches a of log y equals L. And that says that we can interchange log as continuous. Then we can write this as log of the limit as x approaches a of y is equal to L. Then I can exponentiate both sides, cancel, and we get that the limit as x approaches a of y is equal to e to the L. I have like 3 minutes. I can do one example. Yeah, let's do this one. The limit as x approaches infinity x. Before I start, note 1 plus 1 over x is equal to x plus 1 over x, and therefore 1 over 1 plus 1 over x is equal to x over x plus 1. I'm going to use this in my calculation, and then everybody says, where does this come from? So I started writing it out ahead of time. I have that this is exactly 1 to infinity type, just like I had talked about. So what am I going to do with this? I'm going to let y equal then log y is equal to, I'll apply natural logarithms to both sides. That will say that the natural log of 1 plus 1 over x to the power x, or log y is equal to x times the natural log of 1 plus 1 over x. Therefore, I want to take the limit as x approaches infinity of log y is equal to the limit as x approaches infinity of x times ln 1 plus 1 over x. This is now 0 times infinity type. So I can do 1 over whichever one I want. I'm not going to do 1 over log plus 1 over it, so I'm going to do 1 over x. This is equal to the limit as x approaches infinity of log 1 plus 1 over x over 1 over x. That's just using the clever trick of 1 over. Now, this is specifically 0 over 0 type. Therefore, I can use LHospitals rule to take the derivative. This is equal to, by LHospitals rule, the limit as x approaches positive infinity. Now this is what I'm doing. The derivative of log is 1 over the inside. So 1 over the inside is going to be x over x plus 1 times the derivative of the inside, which is negative 1 over x squared, over the derivative of the bottom, which is also negative 1 over x squared. These are going to cancel out. And this will leave me with the limit as x approaches infinity of x over x plus 1, which is equal to 1. Pull out the highest power on the top and the bottom, you get 1. 1 over 1 plus 0. Therefore, this says that log of the limit as x approaches infinity of y was equal to 1. Or if I exponentiate both sides, this says that the limit as x approaches infinity of y is equal to e. i.e. we have, this is probably a pretty good place to end, the limit as x approaches infinity of 1 plus 1 over x to the power x is e. This is our definition of e. Now we just proved it using LHospitals rule. E is this limit. So this is one way to get at this limit now, is using LHospitals rule. The other indeterminate forms of exponential types are the same strategy. You call it y, you log both sides, you can bring this one down, and then you have the e at the end. But all exponential types, whether it's 0 to the 0 type or infinity to the 0 type, this still gives us the same strategy in each case. So I'll do more next Tuesday, but at least there today we've seen in all of its glory all 7 types essentially, or all the categories of LHospitals rule. So have a good weekend. I'll see you on Tuesday.